Kaku uncovers knowledge into an astounding disclosure. The James Webb Space Telescope has perceived an upsetting signal coming from the Andromeda Galaxy for more than a century. How we could decipher Andromeda was by and large earthbound. Yet as of now, equipped with the James Webb Space Telescope, our perspectives are definitively moving. This new data has sent shock waves through established specialists. Anyway, what does this staggering disclosure tell us? And why is it making such a commotion among space specialists? Join us as we dig into the nuances of this exposure and explore how it influences how we could interpret our adjoining universe. Before we dive into the subtleties of the upsetting signal, it's important to see some context about the Andromeda Galaxy. By and large, the Andromeda Galaxy was the first clue that our universe stretches out beyond the Milky Way. This disclosure moved our understanding, highlighting that we may simply be a small piece of an immense universe. At first, the Milky Way was viewed as the entirety of the universe. Early cosmologists, utilizing limited technology, proved unable to separate the Milky Way into individual stars. This changed with Galileo Galilei in the 17th century. Utilizing a telescope, he observed that the Milky Way was composed of various stars. This finding began to challenge the notion that the Milky Way was the universe's only galaxy. The genuine game changer came with Edwin Hubble during the 1920s. Utilizing the Hubble telescope, he saw far-off objects beyond the Milky Way, identifying these as independent galaxies and expanding our view of the universe. One of these galaxies was Andromeda, otherwise known as M31. Its perception traces back to the Persian astronomer Abd al-Rahman al-Sufi in the 10th century, who noted it without the help of adaptive technology. By the 20th century, mechanical advancements permitted astronomers to investigate further. They understood that Andromeda was an undefined cloud with a vast universe of stars, similar to our Milky Way, yet located around 2.537 million light-years away. The investigation of Andromeda has advanced significantly since then. Observations have moved from ground-based telescopes to space observatories like Hubble, and as of now, the James Webb Space Telescope. Each new instrument has brought us closer to understanding Andromeda's true essence. Interpreting Andromeda's plan and association assists space experts in delving deeper into the universe. It serves as a benchmark for our Milky Way, offering insights into galaxy development and evolution. The connection between the two galaxies is significant for understanding the fate of our Milky Way, particularly since they are expected to collide in around 4 billion years. Recently, the James Webb Telescope has captured an upsetting signal from the Andromeda Galaxy. But what does this latest signal tell us? The James Webb Telescope has brought new understanding. This outstanding instrument, vastly better than its predecessors, has captured data from Andromeda that challenges past understandings. The telescope's robust sensors have detected unusual movement in Andromeda Place, fluctuating significantly from previous perceptions. This has captivated researchers around the world. The signal suggests essential processes are occurring within the galaxy, possibly connected with its genuinely massive black hole or recently concealed irregularities. One key finding is the adjustment of Andromeda's mass. Prior estimates stated Andromeda was substantially larger than the Milky Way. However, new data suggests this gap may not be as significant as previously thought. Updated measurements demonstrate Andromeda and the Milky Way are more practically identical in size, reshaping how we could interpret our own galaxy's place. Additionally, the James Webb Telescope has provided clear images and spectra from Andromeda. These have revealed new star formations and chemical structures within the galaxy. Such subtleties are vital for grasping how galaxies evolve and what conditions could lead to life. Another critical disclosure involves Andromeda's dynamic cosmic center. The data shows that the black hole at the center is more active than previously believed. This activity influences the surrounding region and may impact the galaxy's overall structure. Furthermore, the telescope's discoveries address the mysterious dark matter by studying the gravitational effects on Andromeda's stars. Researchers can better understand how dark matter is distributed throughout the universe. This is essential for addressing one of cosmology's greatest mysteries. What is dark matter, and how does it influence the universe? These new discoveries by the James Webb Telescope have prompted various studies. Researchers worldwide are analyzing the data to uncover more about Andromeda's secrets, each finding helping to understand the universe's history and future, providing a clearer grasp of the universe's operations. Andromeda, our closest celestial neighbor, has an array of extraordinary features that intrigue cosmologists and differentiate it from other galaxies. First, Andromeda's size is significant. While estimates have changed, recent data suggests it spans around 220,000 light-years in diameter, making it one of the largest galaxies in the local group, much larger than the Milky Way. Its enormous size contributes to its mass, holding an estimated 1 trillion stars, surpassing the number in our own galaxy. Andromeda's structure is another focal point. It has a regular spiral shape, but with a bulge. The galaxy contains a protruding center surrounded by rings of dust and gas, which are sites of active star formation. These features indicate a dynamic galaxy with ongoing processes that shape its appearance and evolution. The center of Andromeda is especially intriguing due to the presence of a double-peaked surge, suggesting it might host a particularly massive black hole. This is similar to the Milky Way, but the nature and activity level of Andromeda's black hole provide valuable information for understanding these cosmic objects. Moreover, Andromeda is surrounded by a halo of celestial material extending many thousands of light-years. This halo is made of stars, planetary nebulae, and globular clusters, providing evidence of the galaxy's complex development and history. The globular clusters, in particular, are of critical interest. With more than 460 identified, they offer insights into the early stages of the universe's development and the dynamics of star clusters. Another remarkable aspect of Andromeda is its satellite galaxies. More than 20 smaller galaxies orbit Andromeda, some of which are largely stripped of their stars and gas, contributing to Andromeda's growth. This process, known as galactic cannibalism, highlights the aggressive nature of galaxy development and provides a live illustration of how galaxies evolve and interact over time. But how is the Andromeda Galaxy evolving, and what does its future hold? The development and future of the Andromeda Galaxy are subjects of critical interest and exploration in cosmology. One significant aspect of Andromeda's evolution is its potential transition from a spiral to a ring galaxy. Observations suggest changes in the pattern could lead to this intriguing structure. Ring galaxies are fascinating and form under specific circumstances, often following a collision or close encounter with another galaxy. If Andromeda is evolving into this structure, it suggests a history involving interactions with other galaxies. Andromeda's future is closely tied to its interaction with the Milky Way. Estimates predict that in around 4 billion years, Andromeda and the Milky Way will collide and merge. This event, while seemingly catastrophic, is a normal part of cosmic evolution. The collision won't involve direct impacts between stars due to the vast distances between them. However, the gravitational forces will reshape both galaxies during the merger. Gas and dust from the two galaxies will interact, leading to new bursts of star formation. This explosion of stellar creation will illuminate the merging galaxies, creating a unique and magnificent cosmic event. The collision will ultimately result in a single elliptical galaxy, a process common in the universe's history, but extraordinary in human terms, given that our direct involvement in these events is highly improbable. The very massive black holes at the centers of the two galaxies are also expected to merge. This event could result in significant emissions of radiation as matter is consumed by the newly formed black hole. Focusing on this process provides insights into the life cycles of galaxies and the role of black holes in their evolution, the eventual fate of Andromeda, and its normal consolidation with the smooth way means for the destiny of our nearby planetary gathering. While the fact that the planetary gathering makes it unimaginable, its situation and conditions could fundamentally change. This remembers expected shifts in orbit or even removal from the recently framed framework. Grasping these cycles assists researchers with anticipating the results of comparable occasions somewhere else and gives context for the conceivable destiny of our own planet. The investigation of Andromeda's advancement in the future is about figuring out the powers at play and the inescapable movement of cosmic systems over billions of years. The normal consolidation between our system and Andromeda raises critical inquiries regarding its effect on Earth's current circumstance. It is fundamental to grasp that the tremendous distances between stars imply that genuine star-on-star influences are far-fetched. However, the gravitational impacts of such a consolidation would be significant. The consolidation could upset the steady circles of stars and possibly send a significant number of them, including our Sun, into new directions. This change in place could have critical ramifications for Earth's environment. If Earth's distance from the Sun changes fundamentally, it could either heat up or cool off, contingent upon the bearing of the change. A hotter environment could lead to dissolving ice caps and rising ocean levels, while a cooler environment could trigger another ice age. Moreover, the consolidation could lead to increased radiation reaching Earth. As the Smooth Way and Andromeda's black holes approach each other, their interactions could accelerate particles to high energies, increasing the amount of radiation entering Earth's atmosphere. This increase in radiation could have unfavorable consequences for Earth's biological systems, possibly leading to increased mutation rates in life forms and affecting biodiversity. Changes in Earth's orbit or axial tilt could also disrupt the distribution of ecosystems across the globe. Species adapted to specific environmental zones could find their territories unsuitable, prompting shifts in biodiversity and ecosystem structures. Some species could flourish under these new circumstances, while others could face extinction. Furthermore, the consolidation may trigger new star development as gas mists from the two galaxies collide and compact. If this star formation happens close to the planetary system, the radiation from these new stars could also influence Earth's current environment, further affecting climate and life. However, it is fundamental to take note that these events are anticipated to happen billions of years in the future. Human life, as far as we know, may have evolved significantly by then, or our species could occupy various parts of the world or universe. The discoveries from the Andromeda Galaxy have significant implications for understanding our own universe and its future. The comparison between Andromeda and the Smooth Way assists astronomers in better understanding the structure and evolution of spiral galaxies. Observing Andromeda's elements, like its twisting arms and the movement around its supermassive black hole, provides a reference point to focus on similar elements within the Smooth Way. This comparative study refines our models of astronomical elements and development. Additionally, the discovery of Andromeda's size and mass has direct ramifications for how we interpret the Smooth Way. Initial assumptions stated Andromeda as significantly larger than the Smooth Way. However, recent data suggests that the two galaxies might be more practically identical in size than previously suspected. This challenges our perspective on the Smooth Way's situation in the local group of galaxies and its gravitational impact. Although the Smooth Way is presently a barred spiral galaxy, interactions with adjoining galaxies, particularly Andromeda, could change its design. Figuring out Andromeda's development provides hints about the events that lead to such massive changes in galaxy morphology. By focusing on Andromeda's current status and predicting its future direction, space experts can mimic the consequences for the Smooth Way. This includes changes in star development, the distribution of gas and dust, and the dynamics of both galactic centers. The field of astronomy has experienced significant changes thanks to mechanical advancements. From the earliest telescopes to the complex observatories of today, each step forward has expanded how we might perceive space. The journey began with the invention of the telescope in the mid-17th century. This simple device, consisting of lenses within a tube, allowed astronomers to observe the moons of Jupiter and the phases of Venus. Over time, the complexity and power of telescopes increased. The 19th and mid-20th centuries saw the development of larger, more powerful telescopes, which permitted astronomers to see further into space and to discover new celestial bodies like Neptune. However, these ground-based telescopes had limits, primarily due to atmospheric interference and light pollution. The launch of the Hubble Space Telescope in 1990 marked a significant leap forward. Situated above Earth's atmosphere, Hubble provided clearer, further perspectives on our universe. The universe, at any other time, has prompted leaps forward in the way we decipher dark matter, the age of the universe, and the advancement of space. Following Hubble, other space telescopes, including the Chandra X-ray Observatory and the Spitzer Space Telescope, have observed the universe from space. Notwithstanding optical telescopes, radio, Infrared and X-ray observatories have extended our vast toolkit. These instruments permit stargazers to distinguish and study peculiarities like the universe's microwave background radiation, star formation areas, and the remnants of cosmic explosion blasts. Dark matter remains one of the universe's greatest secrets, undetectable, yet comprising a critical piece of a galaxy's mass. Dark matter doesn't transmit, retain, or reflect light, making it undetectable by conventional means. Rather, its presence is deduced from gravitational effects on apparent matter, radiation, and the large-scale structure of the universe. In Andromeda, proof for dark matter comes from the galaxy's rotational speed. Stars close to the galaxy's edge rotate at comparable rates to those near the middle, which is contrary to what might generally be expected if only visible matter were present. This uniform rotation rate suggests a significant amount of concealed mass attributed to dark matter, wrapping around and impacting the galaxy. Observations of Andromeda also reveal an enormous corona of dark matter extending far beyond the visible stars. This corona influences the movement of satellite galaxies and star clusters orbiting Andromeda. By focusing on these orbital movements, space experts can estimate the mass and distribution of dark matter within the galaxy. Such examinations show that Andromeda's dark matter corona is both massive and extensive, expanding more than 1 million light-years from its center. The distribution of dark matter in Andromeda isn't uniform. It is denser near the galaxy's center and becomes less dense outward. This dispersion influences the formation and evolution of stars and gas clouds within the galaxy. Dark matter's gravitational force helps shape the winding arms and impacts the rate and location of new star formation. Moreover, dark matter is believed to play a significant role in galactic collisions and mergers. The impending collision between Andromeda and the Milky Way, for example, is also a product of the massive dark matter coronas surrounding both galaxies. The dynamics of this impact, including the potential condition of the merged galaxy, will be significantly influenced by dark matter. The new discoveries from the Andromeda galaxy have significant implications for how we interpret the universe. Andromeda's findings provide pivotal information on galaxy formation and evolution. By observing Andromeda's structure, astronomers gain insights into how galaxies develop over billions of years. This includes the formation of spiral arms, the evolution of central bulges, and the role of impacts and mergers in shaping galaxies. Understanding these processes in Andromeda helps cosmologists develop more accurate models of astronomical development across the universe. Andromeda's discoveries also contribute to the refinement of the cosmic distance ladder by measuring distances within Andromeda and comparing them with those from other galaxies. Space experts refine the techniques used to determine vast scales. This is critical for assessing the expansion rate of the universe, an essential parameter in cosmology known as the Hubble constant. Moreover, the investigation of Andromeda's stellar population and chemical composition offers insights into the life cycles of stars and the distribution of elements across the universe. These findings help cosmologists understand the cycles of nucleosynthesis and chemical evolution that occurred in the early universe and continue to happen within galaxies. Space exploration, while advancing our knowledge and technology, presents environmental challenges. The launch of rockets, for instance, releases pollutants into Earth's atmosphere. Rocket fuels emit chemicals like chlorine and alumina, which can harm the ozone layer and contribute to atmospheric pollution. Debris is another critical issue. Space missions leave behind flotsam and jetsam or space junk, ranging from spent rocket stages to broken satellites. This junk orbits the Earth at high speeds, posing impact risks to operational rockets and satellites. Efforts to track and eliminate space debris are ongoing, but the increasing number of objects in space makes this a complex environmental test. On planetary surfaces, contamination is a concern. Rockets visiting different planets or moons can carry Earth organisms, risking the contamination of these environments. This is especially crucial in the search for life, as introducing Earth life can complicate the detection of native organisms. Space missions must adhere to planetary protection protocols to mitigate this risk, ensuring that spacecraft are sterilized and missions are carefully designed to avoid environmental contamination. Light pollution is a frequently neglected outcome of space activities. Satellites and large star constellations, like those used for global internet coverage, reflect sunlight back to Earth, obstructing cosmic observations and altering the night sky. The investigation of the Andromeda Galaxy offers significant insights into the universe's structure, development, and future. By comparing Andromeda to the Milky Way, cosmologists gain a better understanding of galaxy dynamics. Observing Andromeda's characteristics, such as its spiral arms and massive black hole activity, provides a reference point for examining similar features within the Milky Way. This comparative approach refines our models of galactic dynamics and evolution. Additionally, the discovery of Andromeda's size and mass challenges previous assumptions and reshapes our perspective on the Milky Way's place in the local group of galaxies. Understanding Andromeda's evolution provides clues about the events that lead to significant changes in galaxy morphology. By reconstructing Andromeda's current state and predicting its future trajectory, space experts can anticipate the impacts on the Milky Way and refine models of galactic evolution. However, space exploration also presents environmental challenges, including pollution and contamination, which must be addressed to ensure responsible exploration and the preservation of space.